thank you for the invitation first and the opportunity to present this work here. So I will talk about vortex filament solutions for the Navier-Stokes equations. This is a joint work with Jacob Bedrossian and Benjamin Harrop-Griffiths, who are in Maryland and UCLA. And I messed up the alphabetical order, but it should be Jacob first and then Benjamin. So, oops. Yes. The outline of my talk will be the following. I will first discuss a little bit the physics of vortex filaments. So sort of, you know, what to expect from the physics point of view. Then I will describe the mathematical challenges which arise. I will state the theorem that we were able to prove, and then go over some of the ideas of the proof very superficially, but try to indicate you a few ideas. Okay, so let's start with the physics. And maybe we should start by writing down the equations in case you never saw them. So the Navier-Stokes, so in the whole talk, we will be mostly worried about the three-dimensional Navier-Stokes equation, but the two-dimensional problem will also play an important role. And we will view the two-dimensional problem as sort of embedded in the three-dimensional problem. So here I wrote the equation in velocity form. So here U is the velocity of the fluid, P is the pressure, mu is the viscosity. So most of the time we can think of nu as being 1, but I try to keep nu around so that it's possible to compare physical parameters. So that's the velocity form. And the vorticity form of the equation is an equation on the vorticity omega, the curl of U. Maybe the one thing that will come back later is the fact that for us, it makes sense to study the equation in vorticity form, because the geometric structure is more apparent in vorticity form. And then you need to recover U from omega. This is done through the Biot-Savart law, which I wrote here, but here you should switch the roles of U and omega. Okay, so that's the equations that we want to study. And we want to study a specific type of solutions which are called vortex filaments. So vortex filaments are solutions for which the vorticity, so the curl of the velocity, is concentrated on a 1D curve. So the vorticity lives on a curve, and so it should be mathematically understood as a measure. So vortex filaments are expected to be stable. So there are many experiments where you see them, where you see that they are stable, and you also see that they play an important role in organizing the dynamics, which is sort of a loose statement, but in a way, they seem to appear as sort of attractors of the dynamics. And for this reason, it's important to understand them. So I put a nice picture of somebody vaping, and you see this circle is usually modeled as a vortex filament. So I guess we see from there that vortex filaments are stable structures, otherwise they could not be observed. So there is another amazing video that I'm going to try and show you. So let's see if I can get it. Yes. So it's up. So you see, it's dolphins which are playing with vortex filaments made up of air bubbles. And
wow, look at that enormous dolphin!
These are very stable structures, and the dolphins can do very nice things with them. Okay. So back to this. Whoops. Okay. So the basic problem is that ideally you would like to study vortex filaments for the Euler equation, which is Navier-Stokes with zero viscosity. But then it's naively, and apparently not in any reasonable way, not possible to make sense of the equation. So Euler's equation does not support solutions whose vorticity is supported on a curve. This is not true in 2D. So in 2D, there is a singular limit that you can take, and that we will come back to. But in 3D, it doesn't seem possible. So there are two possible solutions, two ways out of this problem. One is to look at Euler's equation, that is take the viscosity to be zero, but replace the filaments by tubes. That is, you thicken the filaments a little bit, and the vorticity is not supported on a 1D object, but on a very thin 3D object. It seems difficult, so we chose rather the plan B, which is to look at Navier-Stokes, so take a positive viscosity. And of course, what's going to happen is that if initially the vorticity is supported on a filament, then it will spread as time goes by through diffusion. And thus the filaments that were initially supported on a 1D curve will immediately have full support. And so I guess physically this makes more sense to take a positive viscosity. But in a way, the geometric structure immediately becomes fuzzy. Okay, so what we went for is solution 2. Okay, so now I'm going to try and talk about the microscopic structure of a vortex filament. So there are sort of a 2-scale problem. On the microscopic scale, what we're going to see is the filament thicken through diffusion. And on a macroscopic scale, what we'd like to do is describe how the geometry of the filament evolves. So on a microscopic scale, the structure should be given by the Lamb-Oseen's vortex, which is a 2-dimensional structure. So for now, we're going to think of a situation where everything happens in a horizontal plane, which is the x1, x2 plane. And everything is invariant in the vertical direction, which is z. So in velocity formulation, the Lamb-Oseen's vortex is given by this formula. So you see, initially, U0 is this object. And as time goes by, the viscosity in U is going to smoothen the velocity close to 0, where there was a singularity, and that's what comes out. It's more instructive to look at what happens on the vorticity formulation. On the vorticity formulation, what you initially have is that the vorticity is just a delta function. So the vorticity is just a delta function along a vertical line. And as time goes by, the vorticity spreads along this Gaussian profile. So this Lamb-Oseen vortex is an exact solution of the Navier-Stokes problem. And it's an exact solution of the heat equation even, because actually the convection term vanishes. So this solves the problem as long as the vortex filament is just initially given by a straight line, right? If the vortex filament is given by a straight line, what you see is exactly that. But of course, this is very rigid. If you try to bend a little bit the vortex filament to have a curve, this doesn't work anymore, and then we have a problem. It's not an exact solution anymore, but we believe that microscopically, that is, if you zoom in on the vortex filament, things should look like the Lamb-Oseen vortex. So as you zoom in, the filament becomes more and more straight, and what you should see is this Lamb-Oseen structure. So the two pictures here are a picture of the, this is the vorticity profile, which is just a Gaussian spreading. And this is the velocity profile, where you see there is this regularization at the origin. Okay. So this is for the microscopic structure. As soon as you turn on the viscosity, what you see is very close to the vortex filament. You see this Lamb-Oseen vortex. Now, how about the macroscopic dynamics? So let's start with the two-dimensional case, which has been solved. So initially, suppose you have a number of vortices which have the position pi of 0 and the strength alpha I. So if you try to embed this in a three-dimensional picture, it just corresponds to a number of straight lines, each carrying vorticity. Now, as time evolves, the positions of the vortices will evolve. So they were initially at position pi of 0, and at time t, they will be at position pi of t. And so since this is the macroscopic dynamics, I got rid of the microscopic dynamics, which is this spreading occurring through viscosity. But to recover the full solution, you should add to this omega, you should convolve it with the heat kernel, basically, to have this microscopic dynamics that is spreading. However, what happens is that in 2D, you can take the limit nu to 0 and get a dynamics for point vortices in the Euler equation. And the dynamics is given by the Helmholtz-Kirchhoff equations. So this tells you how the position of point vortices evolve. So the ith vortex is moving by a velocity given by all the other vortices, but it is not talking to itself. So that's the non-trivial piece when you take the singular limit nu to 0, that the ith vortex is only going to see the field created by all the other vortices through Biot-Savart's law, but it's not going to talk to itself. So this can be rigorously established. So this has been done by Marchioro and Pulvirenti with improvements by Thierry Gallet. So in a way, in 2D, we have a full picture. We know that microscopically, what you're going to see is point vortices, which are thickening out through just the diffusion. And macroscopically, you have this Helmholtz-Kirchhoff equations. Of course, we'd like to do the same in 3D, but this is more difficult. So in 3D, there is a conjecture, but there is no theorem. So first, what sort of data do you put? So the data is omega naught here. So you see, gamma naught is a smooth curve. You put a delta function on this curve, so it's just a superficial measure. Alpha is sort of the strength of the vorticity, and tau is the tangent to the curve gamma naught. Okay, so ideally we'd like to perform the same limiting procedure as in 2D, and say that you can actually send nu to 0, and the outcome is another vortex filament now along a curve whose shape evolves with time. Now this cannot happen in as simply as in 2D. You do have to rescale time, but before getting there, let me explain just the geometric notation. So gamma is the curve along which the vorticity is supported. And at each point of this curve, we have a Freinet frame, which is given by tau, the tangent to the curve. N is the normal to the curve, so it's the second derivative if you take a parametrization of the curve. And then you choose B, so that tau NB is an orthonormal basis in 3 dimensions. So that's the Freinet frame. And you see that the vorticity is always pointing parallel to the curve in order to ensure that the divergence-free condition is satisfied. Okay, so the conjecture here is that if you properly rescale time as you let nu go to 0, the dynamics of gamma are given by the binormal flow. So this was derived, I think, by Darius, who was a student of Levi-Civita, beginning of last century. So the binormal flow is a Hamiltonian geometric flow. So if X is a parametrization of your curve, you see that at any given point of the curve, you go along the binormal, hence the name, and you do so with a strength that is proportional to the curvature kappa of the curve. So that's a very beautiful conjecture that in the appropriate singular limit, the dynamics of the curve gamma is given by this geometric flow, but it's, I would say, completely open as of today. But if you think of the nice pictures with the dolphins, you remember that the vortex filaments often looked like circles, and circles are like solitons of the binormal flow. So at least superficially, it looks like this conjecture is working. Okay, so that was for the physics. So to summarize, there is this microscopic structure which is given by the Lamb-Oseen vortex, and macroscopically, ideally we would like to take a singular limit and derive this binormal flow, but this seems pretty much out of reach for the moment. So what we did with Jacob and Benjamin was just to establish the existence of solutions of Navier-Stokes for data whose vorticity is supported on a curve. This is already a big challenge, and I'm going to try and explain why. Okay, so our aim, as I was saying, was to construct solutions of the Navier-Stokes equation for data which are either given by so this is the straight filament plus a smooth perturbation, or this is a curved filament along a curve gamma naught to which you add a smooth perturbation. So of course, if there was no perturbation in the straight case, we know that the solution would be given by the Lamb-Oseen vortex. But if you add a perturbation, this destroys this exact structure and things become complicated. Now, if you think of the curved case, even in the absence of a perturbation, it's not clear at all that the Navier-Stokes equation admits a solution. Okay, so let me maybe explain why this is difficult. Okay, we're going to go through, the theories that exist about solutions of the Navier-Stokes equation. The first theory that was put forward is due to Leray. Could it apply to this problem? Well, the answer is no, because as we know, Leray's theory deals with finite energy or solutions, which is to say solutions whose velocity is square integrable. And if you think of the Lamb-Oseen vortex, remember that U0 looks like is x perp over x squared, which is not integrable in dimension 2. Okay, so Leray's theory and its extensions to locally integrable, locally L2 velocity fields cannot apply. So we need to do something else. Well, of course, the next step is to turn to strong solutions. So strong solutions, as we know, the optimal framework for strong solutions is given by functional spaces which are scaling invariant. And so let's just immediately go to scaling invariant spaces and see if this might work. So historically, Fujita Kato was about H1/2 in 3D, and Kato about L3 fields. Could these theories apply? Well, no, because once again, U0 misses these fields by quite a bit. U0 misses these functional spaces. Okay, so there was a number of improvements, but let me get to the optimal framework, which is, as you know, Courant-Tatarus theory. Could it apply to this framework? So Courant-Tatarus theory was about data which are gradients of BMO functions. And the good news is that the Lamb-Oseen vortex is the gradient of a BMO function. Well, now the bad news is that if you look precisely at Courant-Tatarus theorem, it requires that either you are the gradient of a BMO function and you are small, or you are the gradient of a BMO function, and the distance to a Schwartz class function, say, is small. But this is not the case for this Lamb-Oseen vortex. As soon as you put some alpha, which is large, in front of it, of course, if you want to compare to the viscosity nu, the Courant theory is going to apply if alpha, so the strength of the vorticity, is much less than square root of nu, which is a perturbative regime. Okay, so Courant does give the existence of solution, but only in a perturbative regime where alpha is much less than the square root of the viscosity. So the strength of the vorticity is much less than the square root of the viscosity. So this makes sense. You know, we know that strong solutions can only deal with perturbative regimes, but physically the interesting case would be alpha large. So we need to do something else. So of course, in all this discussion, I just focused on the Lamb-Oseen vortex. But if instead you think of a curved filament, it's going to work exactly the same, because microscopically what you see is the Lamb-Oseen vortex. Okay, so actually there is a good reason why you know, the classical theories do not apply, is that the data we are dealing with are really at the boundary of what you can do through a perturbative approach. And one way of making this rigorous, say, is through this conjecture of Gia and Chirac, that if you take self-similar data, so data that are invariant by the scaling of the equation, then if you choose a U-naught properly, and if U-naught is self-similar, you might have two different solutions of Navier-Stokes emerging from this data. So now we go back to what we have and we realize that the Oseen vortex is locally self-similar. I mean, the Oseen vortex is exactly self-similar, but if you think of the curved filament, you are sort of locally self-similar. And being self-similar means that, you know, things get complicated and dangerous, and you might have maybe non-uniqueness coming up or some sort of instability. So you can not just apply a naive fixed point argument or a perturbative argument. So this remains a conjecture. Of course, non-uniqueness does hold, as was proved by Buckmaster and Picol for the Navier-Stokes equation, but it's at a much lower regularity, something like L2 instead of H1/2. Now, this conjecture of Gia and Chirac applies to self-similar data, which are a little bit pathological. Yeah, they are designed to sort of have a problem. And we believe that the Lamb-Oseen vortex, since it's a physically relevant solution, should be more stable and should not have this type of problem. But of course, this has to be shown. Right, so what I'm saying here is that if you have self-similar data or locally self-similar data, under a smallness assumption, then you expect to see local well-posedness, as was proved by Courant and Taru. But if locally self-similar data are not small, then, you know, bad things might happen, as was conjectured by Gia and Chirac. And this explains why our problem is hard. If you take alpha, there is a typo. If you take alpha much bigger than square root of nu, as soon as you escape the perturbative regime for locally self-similar data, things become difficult. So in 2D, you have the same picture, but in a way, locally self-similar data have a nicer geometry. Basically, they are of the type, the vorticity is supported at a number of points. That's basically the only reasonable way you can be self-similar, because if you think of 1 over x squared, this has the good scaling, but this is not distribution. I guess you could think of even more complicated objects, but basically the only interesting self-similar objects in 2D are given by delta functions. And it has been shown that Navier-Stokes is locally well posed for data of this type, so a bunch of delta functions plus a perturbation. And even it's been improved to omega naught being a finite measure. And this allows for locally self-similar data. So this has been done by several people. Let me mention Gallet-Wayne, Gallagher-Gallet, and Gallagher-Gallet-Lyons. All right, so in 2D, the situation has been completely clarified, but in 3D, this is not the case. Okay, so now let me state our main theorems. The first theorem is about the straight vortex filament. So both theorems are joined with Jacob Bedrossian and Benjamin Harrop-Griffiths. So the straight filament, remember the geometry is that you have symmetry in the vertical direction. So the filament is just a straight line, and the vorticity is supported on this vertical line. So if there was no perturbation, then we would get exactly the Lamb-Oseen vortex. But now we turn on the perturbation, and it's not clear at all what happens. So our result is that for such data, you have a local well-posedness theory, in the sense that you can construct a solution that depends smoothly on the data and that is unique in an appropriate class. So this is what you expect from local well-posedness. Right. So our second result deals with more involved geometry, where now the vorticity initially is supported along a curve, which is one-dimensional. As always, alpha is the strength of the vorticity, tau is the tangent to the curve, to which you might add a smooth perturbation. But even without a smooth perturbation, the theorem is difficult. And then same thing, you have a local well-posedness result that says that there exists a solution. It depends smoothly on the data, and furthermore, it is unique in an appropriate class. Now, how does this solution look like? Well, like you would expect, that is, the initial filament gets thickened by the heat equation. So you just convolve with the heat kernel. Oh, maybe I messed up the normalization. So you convolve with the heat kernel, and the result is that locally, the solution looks like the Lamb-Oseen vortex, of course, glued on the curved filament, plus a smooth perturbation. So this is saying that the microscopic structure is the one you would expect. of course, the next step would be to say something about the macroscopic structure, meaning, you know, a possible singular limit where you would have a deformation of the curve, but you know, this seems out of reach for the moment. I should say that it's interesting, of course, to prove that you do have this microscopic structure. Physically, it makes a lot of sense, but even mathematically, you have to describe this microscopic structure if you want to prove the theorem. If you're not able to say what happens close to the curve, you cannot analyze this regime, which is locally self-similar. So it's not only you know, the icing on the cake that you can describe the microscopic structure. It's actually very important to understand the problem. Okay, so in the time that is left, I will present some of the ideas of the proof. So I will first discuss how the solution is constructed. So the basic idea is that, so this is a, oh yeah, maybe I forgot to say, as far as the theorems go, the theorems apply for any value of alpha and nu. So you have implicit constants that depend on alpha and nu. Maybe T is going to depend on alpha, the strength of the vorticity, and nu, the viscosity. But you can always get a local solution irrespective of what alpha and nu are. So this goes beyond the Courant data row result. Right. So there is this two-scale structure, right? Close to the filament, you expect to see the Lamb-Oseen, and away from the filament, you just have the sort of background, and both do not really interact except through the velocity, which is recovered through Biot-Savart's law. So that's sort of the main idea. In order to formalize that, we're going to introduce self-similar coordinates just in the horizontal direction. So I should say, let's start with the straight filament. So we just have a filament which is along a vertical line. The filament is a vertical line. The horizontal coordinate is x, and to this horizontal coordinate we apply this self-similar scaling. Now, as far as the vertical coordinate goes, we leave it untouched. Okay, so this makes sense because this Lamb-Oseen thickening is only happening in the horizontal direction. And now we decompose the solution into three pieces. So the first piece is the Lamb-Oseen vortex. And then there are two other pieces. One is a core contribution, which is living on the same scale as the Lamb-Oseen vortex, and which is, for this reason, best expressed in self-similar coordinates, tau and xi. So that's what's happening very close to the filament. And then there is a background contribution. Oops, sorry. So the background contribution is what happens away from the filament. And then there is no need for a self-similar rescaling there. Okay, so we're going to solve separately for these pieces. So as far as the core filament goes, it solves this equation. So what does this equation mean? Let us unpack it. So omega c is the vorticity close to the filament in self-similar variables. Omega g is the piece coming from the Lamb-Oseen vortex. So it's like the main piece, and then there is a correction given by omega c. U is the velocity, which is expressed in self-similar variables, and therefore is capitalized. And this velocity, it is reconstructed through Biot-Savart's law from the two pieces, the background piece and the core piece. I mean, the three pieces: background piece, core piece, and Lamb-Oseen vortex. And now this Fokker-Planck operator L is what happens. Right. So this Fokker-Planck operator L comes from seeing the viscosity, the dissipation in self-similar variables. So this is what omega c solves. And as you approach minus infinity in the rescale time, which is to say 0 in the physical time, omega c is 0. Okay. So this is what the core is solving. And of course, the first thing to do is to understand the linearization around omega g, which is the big piece in there. So the linearized problem for the core is as follows. So omega c means the horizontal component of the core vorticity, and omega z is the vertical component of the core vorticity. So in both cases, you have the Fokker-Planck operator coming from the viscosity. And then you have gamma and lambda that come from linearizing around the Lamb-Oseen vortex. Okay, gamma and lambda, they have pretty ugly formulas. So maybe I don't need to enter into that. But the great thing is that they were already analyzed in papers by Gallet-Wayne and Gallet-Maekawa. So we were able to rely on these papers to understand the spectral properties of gamma and lambda. And the beautiful thing is that you have this sort of decoupling between omega c and omega z, up to this error, which I put on the right-hand side, and which is time integrable, so which can be treated perturbatively. So the great thing is that really you have this decoupling arising. Oh, there's a typo, it should be a Z here. So you have this decoupling, and each of the two equations that we have already was analyzed in the papers I mentioned. So for instance, let me just say how the spectral theory for L plus alpha lambda can be studied. This is in the paper by Gallet-Wayne, and it's a very nice argument. First, you use rotation invariance. So you want to exclude essentially large unstable eigenvalues. So by rotation invariance, you can look for eigenfunctions that split into radial and angular parts. The radial part satisfies an ODE, from which we deduce that if you have an eigenfunction, then it has to decay fast. So this justifies the manipulations that we are about to do. And then you use the fact that if you are in this weighted L2 space, the Fokker-Planck operator is symmetric, while the capital lambda operator is anti-symmetric. So if you do an energy estimate in this weighted space, you can deduce that any eigenfunction has to be associated to an eigenvalue with a bound that comes from the spectrum of the Fokker-Planck operator. So this is a very nice argument that is in the paper by Getaway. Okay, so now that we wrote this linearized problem for the core, there is much work to be done to put all of this together and solve this nonlinear problem. I'm skipping many details here, so that's not a simple thing to do. And then you can solve for the background. So the background, once again, it's only connected to the core through the velocity u and Biot-Savar's law. So that's okay. Here there are other details which I also skip. So this tells you how to deal with a straight filament, but now the most interesting case is that of curved filaments. So the basic idea is to use a change of variable to change the geometry from whatever shape the filament has back to the straight filament. So we choose this specific map that maps the straight filament to a curved filament through the Freinet frame. It's convenient. And so the idea is that it should map the microscopic structure of the straight filament to the microscopic structure of the curved filament. But of course, there might be problems coming from the change of geometry. So what you're doing is you're sort of pulling back the equation. So the physics happens on this side of the map phi, and we want to pull it back to the straight filament. So we map the physical velocity to the velocity v in the new coordinates, omega, the physical vorticity, to eta. And then, of course, the problem is that the differential operators also have to be pulled back. And this introduces quasi-linear corrections to the Laplacian that appears in the viscous term, but also the curl that appears in the Biot-Savart law. And overall, the Navier-Stokes equation becomes this equation here. So there are a couple of miracles along the way, in that the convection and vortex stretching terms don't see this change of coordinates, but the viscous term does see it. So of course, this is potentially very dangerous because the corrections are at top order in terms of derivative. And so one has to look very precisely at the structure of Laplacian phi and curl phi and check that close to the core of the filament, essentially Laplacian equals Laplacian phi, which means that the quasi-linear terms vanish, and they have to vanish at sufficiently high order that the analysis go through. So this is very delicate, but things work out. So that's all I wanted to say. Thank you very much for your attention.